Okay, welcome to the first review session for our data networks class with Akinlar. And so we're going to just kind of go through some of the questions. And yeah, if you guys have specific questions in mind that you want to kind of cover first, we can. Otherwise, my plan was honestly just kind of going from start to end, pretty much all the questions, and going from there. So feel free to stop me at any point. And yeah, we ready to lock in? Yep, I felt that.
And I can do whatever the fuck I want.
All right, so anyway, the way that Akinlar said that the test was going to be broken down was a lot of it is going to be short answer questions, so a lot of these guys over here. We're definitely going to be having some of these kinds of questions where we have to do like the actual calculations for propagation delays and whatnot. These are not as bad as I had originally thought, honestly. So honestly, it's kind of just memorizing the formula. Legit, just like write it down like a million times, and like you'll kind of get that. Um, yeah, most of these kind of once you get the gist of them, they're pretty much the same formula over and over again. Then we go more into Unit 2, where, remember, this was more of an introduction. Now this is like the linked layer, which is like the first main layer that we're talking about. We kind of skip over the physical layer a bit. We mentioned it a little, but again, the short answer questions are really important to focus in on. But there's also going to be a lot of
আমার একটা স্ট্যাটিস্টিশিয়ান আছে তো আমার মনে হলো আপনি আসা পর্যন্ত আমি এটা লাইক কি করব ডিসকর্ড স্টাডি সেশন বাট আপনি যদি চলে আসেন আমি এখন লিভ হয়ে যাবো
oh yeah, if you guys could just mute yourselves if you're not asking a question or anything. Yeah, so they're also going to have the ones that we'll have to do like CRC, like the kind of the correction bits. I have those on like a separate doc. I just did that on my iPad. And then we'll also have ones where we're going to have to answer some questions like this, right? This is just kind of using a simple formula, very similar to ones before. And then these are the easiest. They're like just a bridge, literally just saying what knowledge we know already. This is definitely going to be a question on the exam. And then finally, one of these bridge spanning trees. These can be a little tricky at first, but we're going to go through them, so we should be good with that. All right, so with that being said, let's get started. And we're going to be starting out with our short answer questions on Unit 1, right? So we're starting out with propagation delay, right? We went over propagation delay and transmission time. And both are kind of similar, and they're easily confused, but they're mentioning two different things. Propagation delay is literally talking about how long it takes you to get from one node to another. So if, let's say, you're going from here to the moon, that's obviously going to be a lot further than here to Queens College or something like that. So because of that, we base the formula on the length of the physical link. So again, if there's like a huge distance between here and the moon, that's going to be a huge factor over here. We divide that by the propagation speed. Usually this speed is given to us. It's usually like the speed of light, the speed on a copper wire. It's very like stagnant most of the time. On the other hand, right, we're dealing with transmission delay. Transmission delay is a little different in that we are actually putting the bits onto the wires, right? So this is not shipping the bits just yet. This is just literally taking the bits, putting them on the wires. You could think transmission like transport. You could think of it as in like an Amazon depot or something. Like, you know, they're packing up boxes, they're putting them on the wires. Because of that, right, with transmission delay, right, that is going to be instead the length of the message divided by the bandwidth. And we'll get into what these are a little bit more later on when we do questions about this, but this is going to tell you how long it takes you to put a certain message onto a certain width of a wire, right? Because that's really what bandwidth is talking about, the lanes of our wire, how much we can really transport at one time. So again, we want to just really keep in mind two important concepts: propagation delay, that's dealing with the actual physical link, like the distance and the speed. Transmission delay is dealing with the message itself and the bandwidth. So we're loading the message onto the wires. Propagation delay, we are propagating or sending it out. This I got honestly very confused with at first, so that's kind of why I'm like, okay, let's try to, focus in on that, because it's very easily to kind of confuse that, and there's going to be a bunch of questions on that. And part B kind of goes into that. If I am setting one bit to a host in the moon, which of the following is the dominant factor, transmission delay or propagation delay, right? Kind of exactly what I had mentioned before, right? We're going to the moon. This is going to be very far. So the length of the link is going to be super far. Because of that, propagation delay is going to be the main issue. That's going to, even if there is a bit of a transmission delay, the propagation delay is going to be the much bigger problem, because clearly the distance is so huge, it's going to take forever. I mean, even if you're sending something to the other side of the world, even that takes a while. So because of that, propagation delay. On the other hand, part C, if I'm sending 1 megabit to a host in the same room, so distance is not a problem here, then transmission delay is going to be the problem. We don't have to worry about traveling super far distances, but what we do have to worry about is the overhead of actually loading the wires up with what we want to send. And that's comes down to transmission delay, right? The actual message, if it's a big message, small message, however long that is, and the bandwidth that we have to work with. Okay, part D, also very similar. I have a data center where 2 servers exchange huge amount of data. I need to reduce the time it takes for the data to go from one server to another. A friend of mine suggests that I reduce the cable size connecting the 2 servers by half. Another friend suggests that I increase the bandwidth of the cable 2-folds. Which suggestion should I follow? So anytime you hear one of these problems, you want to think, am I having issues with propagation delay or transmission delay? And the hint here is it's a single data center. It's a building. And the servers are within that building, meaning there's no distance between the two, right? Because of that, propagation delay is not going to be the issue. It's going to be transmission delay. It's going to take longer for us to load the wires with what we want to send than actually sending it to the next node. Because of that, we want to focus in on the solution that will help with transmission time. And what do we know about transmission time? It deals with bandwidth, because it depends how wide, how many lanes we have, in a sense, where we could put data on that. So because of that, increasing the bandwidth of the cable 2-fold would be much more efficient in this case. If it was the other way around, right, if it was just something that was extremely far, then reducing the cable size would be more optimal. But then you also have to think about it. Like, if you're going to the moon, how are you going to really reduce the cable size too? Like, you can't just magically make the bits go from one end to the other without passing through that huge distance. So chances are the bandwidth is probably more of a likelier solution that's gonna actually work. So with that being said, right, that would be the answer for that one. We have another space question for E. NASA establishes a lunar base and needs to establish a data link between the control station in Houston and the lunar base. So already again we hear that this is quite far. They only need to send a packet of 1,000 bytes every hour that contains some information about things to get done. They can choose to set a low bandwidth link or a high bandwidth link. Which one should they choose and why? So again, the key things here is it's super far distance, and what we're sending is super small. So because of that, propagation delay is the big issue. It's the distance that we need to fix. The transmission time, who cares if it takes forever, because we're only sending 1,000 bytes. That's literally nothing. Literally, we have photos that take up more than 1,000 bytes. So, I mean, most photos go like for what, like 3 megabytes or something? So, like, this is like literally nothing. Because of that, it would be wasteful to even try to use high bandwidth. Why would they want to spend $1 million on 1 gigabit per second link? That's not going to be very helpful because it's not going to make you go any faster to the moon or back to Houston. So, unfortunately, in this case, the only thing that would really help in this way is if we're able to reduce the size of the link itself, which, that's not exactly the most feasible when we're talking about outer space here. But don't buy the crazy extra bandwidth. This 1 kilobit per second is honestly totally fine. Even if it takes a little bit longer to transmit, remember, you're transmitting and propagating at the same time. It's like you put one thing on the conveyor belt and it's going, and then you put another thing on. So that doesn't even matter at all. That's very negligible. Okay, good up to this point. These were like the propagation questions. Okay, let's go onwards. How many layers does the OSI reference model have? Okay, so remember, we have two main models, right? We have the TCP IP, which is the one that we deal with a lot. That's kind of really standard. OSI is just a reference, right? It's just kind of breaking our existing model down into smaller pieces that kind of shows kind of exactly what's going on behind the scenes. But in reality, when we talk about these things, we break them down into the 5 main categories. So, TCP IP, we went through physical, link, we're going to be learning about networks soon, transport, application. Now, it goes a little further with OSI. We still have physical, link is now data link, network is still the same, transport's the same, but now we kind of separate transport and application by these two extra layers here, session and presentation. So you can kind of think of it as when you have a lot of applications, there's so much that these applications can do. They need extra layers to kind of show that and kind of break that down into pieces. So that's kind of where these guys come into play. Again, literally, there's nothing about any of these layers really on this exam, so just straight up just memorize this. Probably some acronym or something. I'll probably try to come up with that. Maybe ask the AI something. But we use the TCP IP model. This is much more important. This is just honestly very extra. We don't really need all of that extra kind of fluff in there. So, because of that, we do not really deal with that. And again, this is also from top to bottom. So, don't accidentally do it from bottom to top because I'll be honest, I typed it from bottom to top first and then I read, oh, right, I have to actually listen to directions. Okay. But yeah, so now we go into circuit switch and packet switch. So we have circuit switch versus packet switch, right? Circuit switch actually kind of creates a full on circuit. And you can think of it as a single path going from one end to the other. This is good and bad, right? It has overhead that you need to set up the path and whatnot. But it's great because we can guarantee performance. It's not store and forward as in packet switching. Because with that, it's like one packet has to hop to the next router and to the next router. So you're doing store and then forward. You hop. Store into that router, forward, another hop. So with circuit switching, we cannot allocate unused resources to other calls. We must allocate specific resources to specific calls. And this makes sense when you think about it because when you have a circuit switching, it's fully designated. And we kind of go into the two main types that we had looked into before, where we have time division multiplexing and crap, what was the other one? frequency division multiplexing, right? Yeah, so with those guys, right, time division is like round robin. It breaks it up into chunks, time chunks, and you have the entire bandwidth for a small time. On the other hand, frequency, you have the entire frequency, but it's a small fraction because you have to break it up so that everyone gets a fair share. So it's like everyone kind of gets a radio band in a way. And because of that, um, these circuit switch networks, the path is reserved to a specific call. You cannot share it. So unused resources can be very wasteful, which sucks when you have very bursty data that, like, if you're sending a message like, hey, LOL, that's much smaller than, here, I'm going to send you my entire essay. So because of that, we're going to end up with some unused resources that are not used very efficiently. Next, we go into packet switch network. So with packet switching networks, again, we have our packets that we break our data into, just like little boxes, and we ship them. And we're able to be very flexible with the size of this data. We can have smaller packet sizes or larger packet sizes. Smaller is nice because you can pipeline these smaller packages, and that allows you to do a lot more at once. But unfortunately, this also can create problems because we also have the header to payload ratio. So everything needs a header, right? It has, like, think of it like you're addressing a letter. You need to have the destination, you need to have your return address, all that fun stuff. Very much likewise when you have a header on a packet as well. And think about it. Are you going to address an envelope for like a tiny little thing that you're going to ship, like one bit of data? No, it's extremely wasteful. So, because of that, it has smaller packet sizes will have very wasteful, large header to payload ratios. Their header ends up being larger than the payload, the actual data. And this is just a whole bunch of wasted bandwidth, right? You could send a much larger box uh, on that same bandwidth that you would be using to send a tiny thing. So there are pros and cons to it. On the other hand, you're saying, okay, maybe larger packet sizes. That's great for the header to payload ratio, but unfortunately, this sucks when it comes to pipelining because we can't have as much concurrency. We can't pipeline multiple things at once. Think about a conveyor belt and you have like this huge package that's taking up the entire conveyor belt. Like by the time that gets to the next router, you could have put like 5 smaller packages in there. So it's kind of a trade-off. Do you want to send more efficiently or have more header to payload ratio? So that's kind of the trade-off when it comes to these guys. And this is only for a packet switch network, by the way. Circuit switch, you send the whole thing in one go. So it's kind of like you surround the entire thing and you just have it go like follow the leader, like a single line, and the data just follows that line. Okay, next question. In a virtual circuit switch network, can packets belong to the same connection, i.e., communicating pairs follow different paths in the network and arrive out of order in destination? No. Going back to what we just mentioned, we have to make sure that you follow the exact path that you were programmed to follow, right? You can't go out of order. Packet switching can be very flexible, sure. Packet switching can jump between one thing to another. But when it comes to circuit switching, you are on that circuit and you are stuck on that circuit. Think of a raceway circuit or something, right? The cars are not going to go off the track. You hope not. You hope you don't get hit by a car or something. So, because of that, we can have equality of service. And this fixed path will make sure that you always know how fast you're going to get to your destination, right? You don't have to worry about having traffic in a sense, it's just constant. And we also know that we're not going to get any out of order packets because, again, we're in a line. It's as if you're literally walking in a line, like think of like elementary school, right? You like walked in a line to get to like the lunchroom. You had to stay in that order. So because of that, if you were last in line, you weren't going to just cut the line and go first. No, it would be first come, first serve. So because of that, it's good in a sense because we do get that quality of service, although, it can be inefficient at times. Datagram networks, right? So we have in the packet switching networks, there are two main types. Virtual circuits, not to be confused with circuit switching, right? And datagrams. So virtual circuit is very similar to with the actual circuit switching, right? We still have that path. You're still creating a circuit, and because of that, you still have that guaranteed quality of service. You won't have things out of order, but you are dividing things into packets because it is a packet switched network. So you just make sure that your boxes are in order essentially, and everything inside those boxes is all in order. On the other hand, datagram, it's as if you have the post office and they just take all of your envelopes, put them into a like a bin, and then they send them off as they please in a way. So, one might get to its destination a little sooner, one might not. But the key is because you're not in a line, because your destination is not set in front of you as it is in a circuit network, you need to have your address, the source and destination on your header. Think of how you can't send an envelope that doesn't have an address. So, same with a packet. That's the one issue with that. And so, because of that, each packet carries its destination address in the packet header. That is correct. And that's because, again, no path is established. So, you do need that source and destination to know where you gotta go. And the main motivation for packet switching, right, is we divide our larger piece of data into smaller packets, right? They have the entire bandwidth. So, it's as if instead of sending down one conveyor belt, you're sending down multiple lanes of conveyor belts. You split it up, and now you can send however many more packets at the same time. Much more efficient, especially when you have variable sizes. You don't have to worry about this giant package just hogging all of the bandwidth. So, because of that, we're able to be a lot more efficient when it comes to packet switching, which is store and forward. Let me turn off Grammarly. This is getting really annoying. I don't care about my grammar right now. Okay. Next, true or false. If a node needs to communicate only with nodes on the same link, i.e., with another neighbor, physical and link layers are enough. In other words, no network layer is necessary. Justify your answer. This one is tricky. So, at first, you're thinking, okay, if it's on the same link, do I really need a network link layer? Do I really need IP to tell it where to go? I mean, it's a point-to-point link, right? It's just on the same link and everything. So yes and no. Yes, in the fact that yeah, I can get the data to where it needs to go, but I don't know what to do with the data. There is in the header of your packet, right, is a type field. And this type field, the multiplexer demultiplexer, specifies where you're going for your upper layer protocol. For instance, I get a packet, I open it. What am I supposed to do with this? I open up the type fields, and this is like the instructions to the network layer. Like, hey, you're going to use IP. Hey, you're going to use ARP. Hey, you're going to use insert whatever protocol you want here. So because of that, right, we do need the network layer in order to decipher what's kind of going on after we get the shipment. So again, while technically you just need the physical layer and link layer to actually move the bits, you don't know what to do with the bits until you have the network layer, which will decipher the data's meaning through that upper layer protocol. Think IP. Right? If you get an IP packet, it's just a packet. You can't do anything with it until you have the network layer to decipher it. Because the networks layer is the actual one that's going to be doing the IP protocols and whatnot. All right. How wide is a bit on a 1 gigabit per second link? So the way we do this, right, is we divide a single bit by how big this unit is. And with a gigabit, right, that is a billion bits. A megabyte is a million bits. Kilobyte is 1,000 bits. You get the picture. We go exponentially. So because of that, right, we just do 1 divided by a billion. And that is always going to be in terms of seconds wide. So that's saying that, remember, it's 1 gigabit per second. So, 1 gigabit per second. So think about that. In 1 second, 1 billion bits are being sent, which is kind of crazy to think about, but that is modern day technology now. So 1 single bit, what do? Is I take that single bit and divide it by this guy over here. So 1/1 billionth is literally 1/1 billionth of a second is like literally how wide this is, aka 1 nanosecond. This is fine. You don't need to know this is 1 nanosecond. I did not know that it was 1 nanosecond. Okay, question P. Suppose you're developing a standard for a new type of network. You need to decide whether your network will use virtual circuits or datagram forwarding. What are the pros and cons of using virtual circuits? Okay, so here we go. Back to this, right? We're doing packet switching. We know this because we have a choice. Virtual circuits, not circuit switching. Very easy to get them confused. So it's virtual circuits or datagram forwarding. Remember, virtual circuits, it allows us that quality of service. That path has been set. We know exactly how long it's going to take us to make it from one end to the other. Furthermore, we also know that we're guaranteed not to have anything out of order. Think about your lunch line. You're going into lunch, no one's going to skip the line. Well, maybe not a QC, because everyone's going to skip the line for free food, you know? But in virtual circuits, no one is going to skip the line. So, datagram forwarding, on the other hand, and then for the cons of virtual circuits, of course, it's very wasteful if you have bursty data, in the sense of if you're allocating this whole circuit for this data and you're just sending the message, LOL. It's such a waste. Like, you're allocating this whole thing and you send a tiny little message, right? It's good for data that is going to be like one size and one size only. Like if you're sending, I don't know, like if you're just sending like the same document over and over and over again, let's just say. On the other hand, right, datagram, this is better for bursty data. I could put things into little packets. They don't have to be the same size. I could do it all different packet sizes, just like in Amazon, right? You have small packages, large packages in the middle. And this allows it to also be pipelined, right? I can't pipeline with virtual circuits because I'm just going to have the whole thing going. So with that being said, it's not going to work as well, virtual circuits. So it might cause some waste. Also, there's the overhead of setting up the path in the first place, right? Datagram's like kind of just like, YOLO, I'm just gonna go chill, go hop 100 times, get to my destination. I have an address here, so I know where I'm going. Virtual circuits, like, no, if you get off this circuit, then you don't know where you're going because there is no address. I kind of went into this already, right? Time division multiplexing versus frequency division multiplexing. These guys are with circuit switching, right? So with time division, you're breaking the bandwidth, the entire bandwidth, into fractions of time. So with that being said, you might have the control for like a few nanoseconds and then switch to another node to go to a different thing. On the other hand, frequency division multiplexing, you just divide it into like radio bands. So this band goes for you, this band goes for you. You get a band, you get a band, you get a band. And because of that, you get the only a fraction because you are splitting the entire frequency into pieces that each of these guys will have for the entire duration of the call. then we go into service interfaces of a protocol and peer interfaces of a protocol. So service interfaces, you could think of like a servant and a master, right? They are protocols going to the layers above on the same machine. It's a servant serving their master, the higher level. Or it's like your boss at work, right? You're serving the boss. Like the boss says, hey, get this assignment done, and you get that done. What you do, your tasks are your service interface. You can do a spreadsheet or you can do a coding assignment. Maybe your boss wants you to code something in either C, Java, or Python. So those are your service interfaces. You can choose to code in C, Python, or Java. And those will get pushed to your supervisor, who is the upper layer protocol in this example. And for internet protocol, we know this is from the networking layer. We didn't really go too much into this, but we do know that the network layer is meant to send or receive packets to the layer above, the transport layer, which is going to actually handle the transportation itself. And peer interface is a little bit different. This was on the same machine when it came to service interface. Peer interfaces is on a different machine, but the same protocol layer. So when it comes to this, like if let's say it's you and your coworker, right? You're two different people, or you in a different company, let's say, right? You have a friend in another company, and you're just chatting, kind of bouncing ideas off of one another. And you could be like, hey, I'm going to help you out. Here, I can code in C and Java. Oh, that's great. The other person can code in Python and JavaScript, let's say. So those are your service interface, your peer interfaces to each other, since you're kind of bouncing the ideas off to each other. Two different companies, two different people, but the same task involved. It's your peer versus service interface where it's your boss, right? The same company, but higher up. And lastly, how and why do packets get lost during transmission in a packet switched network? Briefly explain. This is because there is no quality of service, right? It's not like how when we have virtual circuits or circuit switching in general, when we have everything kind of in just a single circuit, and we know that immediately it's going to guaranteed reach from point A to point B. Store and forward is a little bit different because you have to actually do your hop and you sit at the router for a little bit before you get forwarded to the next hop. Each router has its own queue. But think about it, just like in a restaurant or somewhere, if there's a lot of people there, the line's going to be pretty long. And if the line is long enough, you get kicked out. There is no room for you to wait in there. And unfortunately, when it comes to here with packet switching, if there is no room in the queue, the packet is simply dropped. It's way too busy. There's nothing we can do about it. So because of that, we just gotta drop it completely. So that's one of the issues as well with packet switching networks. All right. Before we go on to these calculation questions, do we have any questions or anything? Thank you, thank you. Okay. So I figure we can finish these guys off, take a break, and then move on to the link layer. Sound good, or any preference? Okay, well, I'll take that as a yes. Again, stop me at any point. You can interrupt me. That's fine. Alrighty, let me just take another sip of my matcha. I don't have coffee, so matcha's the next best thing. College students run on caffeine, right? Alrighty, so these kind of get a little confusing, but it's not anything too crazy. So once you kind of get the hang of it, it's doable. So before we get started with anything, right, let's just remind ourselves of a couple of the formulas, right? We want to remember the time of the propagation delay and transmission delay. This is going to come in handy. So for propagation delay, we have the length of the physical link divided by the propagation speed. Remember, propagation, that deals with the actual distance itself. It's how long it takes for you to propagate a message from one end to the other. On the other hand, transmission delay is how long it takes you to actually get the message onto the wires themselves, getting ready to be transported. And that's based on the length of the message and the bandwidth. So the width of the wires themselves, in a sense. If they have like a lot of lanes for traveling, that kind of stuff. And another thing to keep in mind is that there's also the latency time, and this is mostly just pretty much adding this together with this together. So if it asks you latency or round trip time or single trip time or any of that stuff, like total time that it takes to get from one end to the other, remember, you have to actually load the message onto the wires, transmission delay, and you have to actually propagate the message to the other side, propagation delay. With that being said, let us get started. So we're starting off by sending a file, right? And this is a file F. It is broken up into M packets. So there is an M number of packets with each packet of L bits. This is being sent over a path of N links. Each link transmits at R bits per second. Anytime you hear bits per second, boom, that's your bandwidth. The network is lightly loaded so that there are no queuing delays. When packet switching is used, the M times L bits are broken up into M packets, each packet L bits. Also assume that propagation delay is negligible. So, with this being said, we don't have to worry about propagation delay. So we're only really dealing with the transmission time itself, and if there is any other things that they're going to mention, which they will. First, we're going to suppose that the network is circuit switched. So remember, circuit, single path. Further, suppose that the transmission rate of the circuit between the source and destination is R bits per second. Assuming T of sub S setup time and H bit of header appended to the entire file, how long does it take to send the file? Okay, so first things first, we know that we have the circuit switch network, and we know that we have our M packets of L bits apiece. The thing is, though, because it is circuit switching, we're sending the entire message at once. So we don't need to worry about it being broken up into packets. It also tells us right here when packet switching is used, they're broken up. So otherwise, it's just F. F represents the entire length of the message. Now, the thing is, we need to incorporate the time for setup and the H bits of the header. So we know that offhand, we're going to definitely need to have the time of the setup, right? Time of setup is going to have to get added to this no matter what. But now we need to figure out the transmission delay, meaning how long it's going to take me to get the actual data onto the wires. And we have all the stuff that we need to do that. Because remember, what is the transmission delay? It's the length of the message divided by the bits per second, or the bandwidth. Well, we know the length of the message is F, but we need to incorporate the header in there as well. So this is going to give us F plus H, right? The length of the message plus the header. And this is going to be the length of the entire message. All we need to do is divide this by our bandwidth, which is given to us as R. So this becomes H plus F divided by R, and we just simply add the setup. So the setup is just, okay, boom, I make the wires, I put it together and everything, and now we actually have to put stuff on the wires, which is this part. Circuit switching is usually the easier one. Packet switching is a little bit different. For part B, suppose the network is a packet-switched virtual circuit network. Denote the virtual circuit setup time by TS. So automatically, when I hear setup, I know TS is going to be added to this, first of all. Suppose the sending layers add a total of H bits to the header to each packet. How long does it take to send the file from the source to the destination? Okay. This time we're breaking it down into packets. So the first thing we need to do is anytime it's packet switched, we got to think about that it's being pipelined. We need to find how long it takes the first packet to arrive. All other packets are going to take n-1, it's going to be n-1 links. Because think about it, every other packet is one link behind the leading packet. So with that being said, we're going to be using the same transmission formula. So that, again, being the length of the message divided by the bandwidth. Now, the bandwidth's not going to change, right? We're still going to have R in here. But now, because we're dealing with the first packet, just the first packet to start with, we're going to not take into account M packets. We're just going to take into account that each packet has L bits. So I'm going to just say, okay, the length of one packet is L plus H. So L bits for that one packet plus the header. This divided by R is my transmission time only for the first packet. So before we incorporated the M, because again, F was M times L. This time we're separating them because the transmission time for the first packet is going to be a little different than the other packets. Now, what I said before about us having n-1 links, right? We want to make sure that we have we want to show that it's one less hop for all the other guys, right? Because these guys are happening with parallel processing. They're happening concurrently with one another. With that being said, I can take the remaining packets, right? So my M packets plus n-1. So this is subtracting the one that I've used here before and showing that I have to do for the remaining parts, I have to take my remaining packets and travel the remaining links with that. So this is just getting multiplied by our original packet. So again, to break it down, we have TS, this is our setup, right? We have plus transmission time for the first packet, right? So this is how long it's going to take for the packet to arrive. Then multiplied by our number of packets M and one less hop, because again, everything is going to be kind of like one behind in a way. So just kind of important to keep in mind that when we have packet switching networks, we want to just kind of break it down into pieces, right? So this is again our first, and then all of our leftovers. So this is honestly a little bit tricky, but it kind of just helps like just break it down into pieces. And then from there, you're good. If you just kind of keep in mind that this is going one one less because, again, m is the total number of packets, minus 1. Boom. If they were 10 packets, the rest are 9. And it's going to just take the number of hops for that, for the rest of them. And the last one is pretty easy, thankfully. It's the same thing, but it's 2 times h bits of header. So up here, right, we added L plus h because we wanted to say the total length of the individual packet. All I'm going to say is L plus 2h because now the header is worth twice itself. So everything else is the same here. Otherwise, that's pretty much there. So just kind of takeaways here. We have our circuit switching, which is where we don't care about the packets as much. We just kind of bundle it all up in this F term. Otherwise, here, when we have that, we break it down into packet 1 and the rest of them. Alrighty, question 3. Suppose 2 nodes A and B are connected via point-to-point link. The length of the link is 10,000 kilometers and its bandwidth is 1 kilobit per second. Assume the speed of the signal on the wire is 3 times 10 to the 5th. Okay, first we're going to calculate the minimum return time for the link, right? So, round trip time. What am I saying? RTT round trip time. So for this, right, I kind of mentioned before with the round trip time, we kind of want to have the time that it takes, and because it's round trip time, we want to kind of keep in mind that we've only been calculating in one direction. So if you wanted to go the other way, it's going to be the same distance, just multiplied by 2. So I know that for this, I'm given the length of the link is 10,000 kilometers, its bandwidth is 1 kilobit per second, and the speed of the signal of the wire is 3 times 10 to the 5th. So I'm not given the size of an individual message. They're asking just for the link itself. So because of that, I don't really care about the transmission time right now, because that's not really relevant. That's based if I have a specific message, which that's going to be part B, spoiler alert. So for this, I care about the propagation. So for this, I'm going to be using our propagation formula, which is going to be the length of the link divided by the speed. And just multiply that guy by 2, because again, round trip time. If I do length of the link divided by speed, this is only one direction. I have to just multiply that by 2. So this is literally, once you got the formula, it's just straight up plugging it in. I took the length of the link is 10,000 kilometers. I just converted that into, like just kind of power of 10. That way it cancels out very easily. Then I realized that I think he is allowing us calculators on the exam. So I don't think you really need to really worry about that. I'll be honest, I had more calculation errors trying to freehand it. So do yourself a favor, just straight up plug it into the formula and just shove that into your calculator. Like don't even take a chance. I kind of took a chance with a lot of these just because, like, I could kind of just check it as well. But then I realized, I'm pretty sure he mentioned that we can have calculators. So just kind of go about that. So literally just I plugged it into the calculator. This is the length of the link, and the speed is given here, 3 times 10 to the 5th, and this is just equal to 0.067 seconds. So again, pretty simple. Once you know the formulas, these are very simple. It's just knowing which formula to use, and then you're good. It could be a little tricky at times, figuring out, but once you're good, then you're good.
Just a quick question. So for round trip time, we only take the propagation delay into consideration, right? We don't worry about the transmission.
So if they're saying minimum round trip time for the link, this is your keyword that you're only caring about the link. You're not caring about a message. If it gave you a message, then you'd care about the transmission time as well. Transmission time is always going to be with a message. So it just depends on the context. There's going to be a question later on that's going to say calculate the minimum RTT for the link if I were to transmit X bytes. If it was together in the same question, then you just simply add the two together, the propagation and the transmission time, and any setup or anything they give you. But for the most part, propagation plus transmission, unless it's broken down like this question here. Again, this is the first part is just talking about the link itself, so propagation time. The second part is saying a specific byte message. This is going to be transmission time.
Oh, I see. I see. Thank you.
Yeah, no problem. Yeah, and then again, this is transmission time, right? So plugging it into our formula, it's the length of the message itself, 1,000 bytes, divided by the bandwidth, bits per second. So one thing to keep in mind is you want to make sure that everything's in the same format. So 1 kilobit per second, this is going to be 1,000 bits, right? Is it one or let me just double check that actually. 1 second. Yeah, 1,000 bits. Okay. Yeah. So this is 1,000 bits, right? And we know that the length, the, wait, I'm sorry, hang on a minute. How long does it take to transmit 1,000 bytes from A to B? Okay, so we want to take into account for this one, right? From A to B, this is taken into account propagation time and transmission time because it takes both to get us from A to B, right? Before, we had just mentioned that this is the physical link itself, the propagation. But now that we're transmitting a message itself on this specific link, we need to actually add them together. So to kind of go over when to use what, again, if it's for a specific link, if it's physical, you're using just propagation. If you're dealing with transmitting a message, if they tell you not to worry about the propagation time, then just do transmission time. But here, they did say a specific link, so there's going to be a physical aspect of it here as well. So with that being said, it's going to be our propagation time plus this is going to be our transmission time. And this is not the round trip time either because it's just saying A to B. If it was saying A to B and then back to A, then multiply this by 2. But if you notice, I didn't multiply that by 2. So again, this is just taken from earlier. And then for the transmission time itself, it's the length of the message, which we know is going to be the 1,000 bytes. And remember, bytes, you want to convert this back to bits because your bandwidth is in terms of bits. This is kilobits per second. If this was a capital B, then it would be kilobytes. So all I do is just multiply 1,000 bytes times 8 bits per byte, and then divide that by the 1,000 for the 1 kilobit per second. So with that being said, right, this just comes out to 0.033 for this part, plus 8 for this part. And that means 8.033 seconds. If you've noticed, the propagation time really didn't take that long. It was the transmission time that ended up actually taking longer because, again, it's based on the actual bytes or bits that are transmitted. So a longer message takes a longer amount of time. And usually when it comes to the physical aspect of this is pretty stagnant, right? Once you have this the length of your link and its speed, like there's nothing you can really do to change that. It's not really like this where it's like different messages are going to be different variables. Before we go on, does that make sense? I know that was a little all over the place, but
Yeah, that was pretty clear.
okay. Glad to hear that. All right, so let's do another one. I think this one is a very similar question to that. Suppose a 100 megabyte per second point-to-point link is being set up between the Earth and a new lunar colony. The distance from the moon to the Earth is approximately 390,000 kilometers, and data travels over the link at a speed of light. So, see, speed of light, this is kind of like very like standard in a sense. So we know that this physical aspect, the propagation time, is probably going to be very consistent no matter the bits that they tell us to transmit. So first we're going to calculate the minimum round trip time for the link. Again, we're dealing with the physical aspect. This is the propagation time itself. So our propagation is the length of the link divided by the speed. So we got the length, 390,000, and we got the speed, 3 times 10 to the 5th. And we know that this is round trip time. So we need to make sure that we multiply this guy by 2. So again, we just kind of plug that in. Again, I converted that into powers of 10, but straight up just use your calculator. And then that gets us 2.6. Now, the second part is going to give us the data itself. A camera on the lunar base takes pictures of the Earth and saves them in a digital format. Okay, we really don't care about the context. We just want to know it's 25 megabytes. Reason I say megabytes and not megabits, capital B. If this was a lowercase b, it would be in bits, as you can tell. Yeah, that was like kind of one that really screwed me up. So just kind of remind yourself, capital B, bytes, lowercase b is bits. So what is the minimum amount of time that will elapse between when the request for the data goes out and the transfer is finished? This line is also very important too because it tells us, are we using round trip time or single trip? We're asked when the request for data goes out, so that's saying from Earth to the moon, and when the transfer is finished. Moon goes back to the Earth. That is a round trip. So whatever answer I get here is going to be multiplied by 2. So I know that for this guy, right, the physical part has already been established, my propagation delay. So I'm going to take my 2.6 and add it no matter what. Then I need to take my so my 2.6, again, this the round trip time is already kind of taken into effect, so we're all good here. Then I need to take my transmission time, and this is going to be my 25 megabytes. So because of this, I want to multiply that by 8, right? Because again, 8 bits per byte. And we know that we're also dealing with megabits per second here. So I don't really have to worry about converting it into bits, right? As long as these two are the same unit, we're good. So once I multiply this guy by 8, now it's in 25 megabits. So with that being said, I just take the length of the message divided by our bandwidth, which is 100 megabits per second, and I just add that to my propagation time. And that is going to give me 4.6 as our answer for that. And the round trip time, right, we calculated that already. That's going to be just this part over here, the propagation itself, right? Because it's 2 times the distance that it takes to propagate the message. All right. Question 5. Consider two hosts A and B connected by a single link of rate r bps. Suppose that the two hosts are separated by m meters, and suppose the propagation speed along the link is s meters per second. Host A is to send a packet of size L bits to host B. All right, express propagation delay, t-prop, in terms of m and s. All right, this is pretty much given to us. Distance divided by our speed. So meters divided by m divided by s, essentially. Likewise, transmission time in terms of L and R, bits, and our bandwidth. So it's just going to be L divided by R. These are just our formulas. Ignoring processing and queuing delays, how long does it take for the last bit of the packet to arrive at B? Okay, so that's saying the entire transmission time, putting it on the wires, plus the entire propagation time of propagating it to the other side. So that's going to be the propagation delay plus the transmission delay. So just these two guys over here. Part D, suppose host A begins to transmit the packet at time t equals 0. At what time t equals t of transmission, at the time t equals t transmission, where is the last bit of the packet? Okay, this just requires us to think about what's kind of going on here. So we begin to transmit the packet at time t equals 0. At this point, right, once we finish the transmission itself, we know that the bits have been placed on the wire. They have not propagated yet. At this point, the last bit is just being placed on the placed on the wire. So it just left host A, and it's beginning to go on the link right now. So at this point, maybe we had some bits that were shipped out already that were propagated, but we know the last bit at the time t equals the time that it takes to actually transmit the bits itself. At the end of that, we know that that last bit was just placed on the wire and is about to begin its journey. So that's what we mean by the transmission time, right? We put them on the wires and then we send them off. So it's like the beginning of the conveyor belts. So that package was just put on the conveyor belts and it's going on from there. Okay, E, suppose T propagation is greater than T transmission. At the time T is equal to T transmission, where is the first bit of the packet? Okay, propagation is greater than the transmission. So, with that being said, right, we know that the time that it takes to actually get from point A to point B is longer than the time that it takes to put them on the wire. So, when we reach the end of the T transmission, we know from before, all the stuff was placed on the wires. Where it is now, we don't know. It's somewhere on the link, though. This is because we know that the transmission time is always going to be less than the propagation time. So if, let's say, it takes 5 seconds to do the transmission, and it takes 10 seconds to propagate. So let's say I transmit, I put it on the wires, 5 seconds has passed. In those 5 seconds, some stuff has begun to propagate, but because it takes 10 seconds to make it all the way from point A to point B, we know that that data must still be within the network, within the wires. It can't be all the way at B yet, because again, 10 seconds have not elapsed yet, only 5 have. So there's still a minimum of 5 more seconds of that stuff until you have the first bit of the packet to reach its destination. So it's kind of going on about the difference between the transmission time and the propagation time and what they truly mean. Okay, and lastly, part F. Suppose that S is equal to 2.5 times 10 to the fifth kilometers per second, L is equal to 100 bits, and R is equal to 20 kilobits per second. Find the distance M so that T prop equals T trans. Okay, so this we're literally just kind of setting up a proportion here, right? We know propagation time, again. We're going to kind of drill this into our brains, right? Propagation time is the length of the link divided by the speed. So this is going to be our distance M that we don't know divided by what is our what is going to be our speed in this case is going to be S. So it's going to give me my distance, which I don't know, divided by my speed. And this is going to be equal to, because again, we want to find the distance that they're equal, to our transmission time. Transmission time is going to just be our length of the message divided by our bandwidth. So 100 divided by our 20 kilobits per second. Again, I want to convert this guy so that way they're all in bits. And for this, right, it's kilobits per second, so this is just going to be 20,000 bits. I just solve for M, and right, just a proportion, you can kind of cross multiply, and then you get M is equal to 1,250. So that would be kilometers, because we're dealing with kilometers. So that is the distance that would make these two guys equal. We're almost there. Just 3 more questions. We'll take a break, and then we'll move on to the next thing. I hope I'm not going like too quick or anything. I just try to make it through like the whole thing tonight. That way, like, you guys like have enough time to kind of go over it like tomorrow and everything, and you don't want to be cramming the night before. Two nights before is fine. Huh?
Is it's only gonna be the introduction and the link layer?
Yeah, literally just these two. That's it. So, like, literally all these questions, which this we're pretty much done with at this point. We're on the last 3 of this one, and then we just have this over here, and that's it. We didn't start networking yet, the network layer yet, so none of this is gonna be on it, so don't worry about that. Yeah, and he already kind of told us like kind of what is definitely gonna be on there. So like a bunch of the short answer ones are gonna be on there for sure. A lot of these calculation ones, there's a high chance that they're gonna be on there. From the linked layer, we're going to go over some more, but there's the tree, the spanning tree one. This one's definitely going to be on there. The bridge table, this one's definitely going to be on there. The ones with the polynomial long division, things like that, those are going to be on there. So, but nothing is too bad. I'll be honest, I think the hardest is probably these calculation questions, because it's like you got to figure out which formula to use, and there's kind of like a lot of options and stuff, but it's not too bad. It's Akinlar. We'll be good. He won't kill us. Hopefully. Right. Suppose 2 hosts A and B are separated over 10,000 kilometers and are connected by a direct link of R equals 1 megabits per second. Suppose the propagation speed over the link is 2.5 times 10 to the 8th meters per second. Calculate the bandwidth delay product, R times T prop. Okay, that tells us exactly what we're going to do. R is 1 megabits per second, and our propagation time, once again, is going to be our length of the link divided by our speed. So what is our length of the link? It is 10,000 kilometers. What is our speed? That's going to be 2.5 times 10 to the 8th meters per second. We need to do a conversion here. So I'm going to just deal with the first one for this, right? I can just multiply kilometers by 10 to get meters, right? And that's going to get me just 10,000 times 10. And I can just divide that now by this, because again, now they're both in meters. So with that being said, I can just do 40,000 and then 40,000 times R. Well, R is 1 megabit per second. So with that being said, right, it's just going to be 40,000 because times 1. Okay, and provide an interpretation of the bandwidth delay product. So this is just saying the max number of bits that can be on the link at any given time. Otherwise, there's going to be a delay, right? So this is saying our propagation time, how long it takes, and then the length, the megabits per second, that's kind of just saying how long it's going to take us. So at that point, it's how many of those bits can be on that link at that same point. And lastly, C, consider sending a file of 400,000 bits from host A to host B. Suppose the file is sent continuously as one big message. So how long does it take for the last bit of the message to arrive at B? Okay, so we know our propagation, right? And what we want to do now is we want to calculate our transmission, right? We want to say the propagation plus the transmission will get us what we need, the answer to this question. So with that being said, we have our, over here, 40,000, right? This is gonna be our propagation delay. And our transmission delay is now going to be the length of the message, 400,000, divided by the bandwidth, right? This is going to be megabits per second, so that's going to be 1 million bits. So it's going to be 400,000 bits divided by 1 million bits. That gets me my transmission time. And all we're going to do is just add together our propagation time. And we get that as our answer. Last two questions, 7 and 8, and then we can take a bit of a break and reconvene after. Consider the packet switch network shown below. The bandwidth of the link between the source and router R1 is 1 megabit per second, and the length of the link is 1,000 kilometers per second, I think. The bandwidth of the link between router R1 and the destination is 100 kilobits per second, and the length of the link is 10,000 kilometers per second. Okay, assume, kilometers, I think, just kilometers, sorry. Assume that the speed of light is 2 times 10 to the 5th kilometers per second. A lot of information here. This time we have a packet switch network. So all the questions before, notice how it says a direct link, single link. These are all our virtual, our circuit switched networks, right? Now we're dealing with packet switching. So remember what we said before, store and forward. Store and forward meaning that I go from my source, hop to R1, hop to R2. Because of that, we're dealing with 2 hops here. So now we need to take into account, we have to do the distance from source to R1 and from R1 to our destination. So this is going to change things up a little bit because now, right, if I'm finding the for the source and my destination here, right, I have to still deal with the hop here. So I'm still going to be dealing with the transmission time. The round trip time for the network. So first things first, we're dealing with the propagation time, right? So this is dealing with the actual physical part of the network itself. If it said round trip time of a message, that's your sign to also add together the transmission time. So again, transmission time dealing with the message, round trip time, when they don't give you a bit number, that's when we are only going to be using propagation. Okay. So with that, right, we want to find the propagation time. So our propagation time, once again, is the length of the link divided by the speed. So what we can do here, right, is we know that the speed of light is always consistent, right? This is saying the speed of light, not to be confused with our bandwidths over here. So I know that I have 1,000 kilometers and 10,000 kilometers. They both have the same speed. It's the speed of light. These are fiber optic cables, likely. Because of that, I can just simply add these two together and divide by the speed. So this is going to be my total distance divided by my speed. Which again, it's physical, so it stays stagnant throughout the whole thing. And that's going to get me this, right? And then again, round trip time, I have to multiply by 2. So multiply that guy by 2, and that gets me my round trip time. Now I'm good to go on to the next part, which is going to give me bits and packets. Assume that the source sends 1,000 packets, each of length 1,000 bytes to the destination. How long does it take for the transmission to complete? This time we have an extra bit of information. We have the 1,000 packets. So very similar to the example that we did before, much earlier on when we were talking about the formulas, we have to take into account that there's going to be our first packet, and then there's also going to be all the other packets. So to find the first packet, we're just going to do the same steps that we've done before. We're going to take our propagation time, right? This time, though, we have to see, we have our propagation time, which that's going to be the same for the entire thing, okay? Because we're going to have to make it to the end regardless. The transmission time is where it's going to get a little different because that's going to depend on whether I'm on the first link or the second link. So each has 1,000 bytes. So we should just do ourselves a favor and convert everything into bits to make ourselves a little bit easier, because again, this is megabits per second, kilobits per second. This is bytes. So what I can just do is I can just do 1,000 times 8, which is just 8,000. And I can say that I'm going to have 1 megabit per second. So that's going to be 1 million bits. And I can just say the length, 8,000, divided by 1 million. And likewise, the second link is 100 kilobits per second. So that becomes 100,000. So 100,000. And that's, again, 8,000 divided by 100,000. So just to confirm, we're doing transmission time. So it's the length of the message, 8,000 bits, divided by our bits per second. So again, this is our transmission time. This was our propagation time, which is just going to be consistent throughout the whole thing. We add them together, and we know that this is going to be the amount for the first packet only. Now we need to take into account all the other packets. There's 999 other packets. So that's where that n-1 comes into, n-1 comes into, which we brought much earlier on. Where now we're dealing with the remainder. The remainder are going to just kind of follow along. But the thing is, it's not going to be at the same rate. If I have both of these links, right, we know the first one is obviously going a lot faster because it's in megabits per second rather than kilobits per second. Mega is going to always be much bigger than kilo. Because of that, I know my first link is going to be much faster, but my second link is going to be much slower. This is going to create a bit of a bottleneck. Think about if you're traveling on a highway and you're speeding, woohoo, no traffic, and then you get into a place where you have to merge where there's construction or something, and boom, you're stuck in a bottleneck of traffic. What's going to take up most of your time? The bottleneck of traffic. So while people are happily going down the highway at max speed, they're also going to have to make it through that same part with the construction. So whenever we do these packets, we take into account the part with the construction, because someone's always going to be on that slower part when someone else is on that fast part. That bottleneck is what we take into account. So we take the 999 other packets, right? And we're going to have to, again, because it's 999, times the transmission time of the slower link. So this is going to be the kilobit link. And each of these guys, we know, taking it right from here, is 8,000 divided by 100,000. So I'm taking my 999 other packets, multiplying the transmissions for each of those 999 other packets by the slowest link that they're going to get stuck at, which is going to be the second link. I get that as 79.92. Now I can put my two things together. I can put the first packet in and then all the other packets that are currently slowed down. That gets me my total answer of 80.063. So this one was a little tricky, but just kind of break it down. We did the round trip time. That's the physical part of it. Add the round trip to break it down into two transmission times. One for the first half, one for the second half. This is going to be your first packet. Then do the remaining packets times your slowest transmission link. Add them together, and boom, you get your answer. All right, last question. Woo. Consider the following network. Bandwidth of the link between A and R1 is 1 kilobit per second. Bandwidth of the link between R1 and R2 is 2 kilobits per second. Bandwidth of the link between R2 and B is 1 kilobit per second. Assume that an application at A sends 10 packets each of size 1000 bytes. Assuming that the transmission starts at time 0, compute how long it takes for the last packet to arrive at B. Ignore the propagation, processing, and queuing delays. Thank goodness. I don't want to be calculating the propagation again. So this is pretty much the same exact problem that we did up here in part B. So we don't have to worry about propagation time. So the only thing that we need to worry about is our transmission time. So each packet, there's 10 packets, each size is 1000 bytes. So I know automatically from the last question, 1000 times 8 means that each of these packets is 8000 bits. So first, let me calculate how long it takes to go on the first packet. Well, this is going to have to go the entire length. So because of that, I'm going to have to take this is the transmission time, so I'm taking the size, 8000 bits, divided by the bits per second, right? We know this is the kilobits per second, so this is going to be 1000. So this is going to be 8000 divided by 1000. Then the next jump. This is 2 kilobits per second, plus 8,000 divided by 2,000, plus the third jump, 8,000 divided by 1,000. Add that together, and it's 20 seconds for the first packet. Now for all the other packets, right? How many packets were there? 10. We shipped 1. We have 9 left. 9 times the transmission slowest link. Our slowest link is 1 kilobit per second. Yes, there's 2 of them. No, it doesn't matter. They're both the slowest links, so we know that's going to kind of take the longest with that. So because of that, we're going to take the 9 remaining packets times 8,000 divided by 1,000, right? This is our slowest transmission time, smallest bottleneck, and multiply that together, right? And that's going to just get us 72 seconds. Add them together. 92 seconds is your answer, and you are done.
Wait, how come for this one we're taking the smallest bottleneck?
Yeah, so actually this probably should say largest, honestly. It's smallest in the sense of the smallest bandwidth, right? So largest bottleneck, aka smallest bandwidth, right? We kind of did the same thing here. We took the smallest bandwidth because this is the slowest part up here, the 100 kilobits per second. That was my 100,000. because 100,000 is smaller than 1 million. So this is my slowest link, so I put that there. This is my bottleneck.
Okay, okay. Oh, okay. Yeah, okay. That makes sense.
Cool. All right, other questions? All right, I am going to stop the recording here. We're going to take a bit of a break, and then we'll move on to the second question set.